Electromagnetic induction lesson 3. In the last two lessons, we did Faraday's law of electromagnetic induction and learned about magnetic flux and how the flux was increasing when a magnet was moving towards a coil and how the flux was decreasing when the magnet was moving away from the coil. Or if the magnet is kept fixed and the coil moves towards the magnet, either north or south, the flux increases. And if the coil moves away from the magnet, the flux decreases. Now let us do a numerical and go to Lenz law that gives the direction of current, induced current. Now the numerical is like this. The magnetic flux phi. Phi I had explained you, phi was equal to B dot A, that was equal to BA cos theta, where B is the magnitude of the magnetic field, A is the area, magnitude of the area vector, theta is the angle between the magnetic field and the area vector. And flux was defined as the number of magnetic lines of force passing through the area normally. If the area is to this side and the magnetic field is to this side and this angle is theta, then these field lines are not passing through this area normally. So in that case, we had taken the cos component of the area. That is, this is your A cos, this is your A sin theta, and this will be your A cos theta. Now A cos theta and B are in the same direction. That is why flux was defined as B A cos theta, because it was defined in the definition the number of lines of force passing normally. So by taking the component of A in the direction of B, now these lines of force, now this and this becomes in the same direction, means the area vector and the field vector are in the same direction. This area vector and this, they are in the same direction, means lines of force due to this B are coming out from A cos theta normally. That is why it was defined like B dot A, that is BA cos theta. Now the magnetic flux phi threading a coil, means passing through a coil, changes from 12 into 10 to the power minus 3 Weber. Weber was the unit of flux, to 6 into 10 to the power minus 3 Weber in 0.01 seconds. Then calculate the induced EMF. In the last lesson, we had derived EMF, induced EMF in a conductor E was equal to minus n d phi by dt, where phi is the flux, how the flux is changing with respect to time. If phi is constant, means the coil is fixed, is at rest, the magnet is at rest, means there is no relative motion. So there is no change of flux, means there is flux, but there is no change of flux. So since there is flux which is not changing, constant, so if phi is constant, derivative of a constant is 0, 0 into this thing is 0, so EMF is 0. So only when the phi changes, either you move the magnet towards the coil or the coil towards the magnet, or you move the magnet away from the coil, or you move the coil away from the magnet, then there is a change of flux, otherwise not. If both are at rest, there is no change of flux. And n was your number of turns. So initial flux phi 1 is given as 12 into 10 to the power minus 3, phi 2 is given as this, small time in which it changes is 10 to the power minus 2 seconds. And we know EMF is equal to E minus n d phi by dt, where negative sign only indicates Lenz law, that I will discuss right now. So just by putting this expression, since there is a single coil, n is equal to 1, so minus phi 2 minus phi 1 over dt, final flux minus initial flux. This negative sign only indicates the direction of current, which I will explain in Lenz law. So just put the value of phi 2 and phi 1 divided by time. This comes out to be 0.6 volt. Now let us come back to Lenz law. This is important. This will give you the direction of current. This Lenz law, this gives the direction of induced current in the circuit. Now this is important. From here to here is important. Now what it is? Now the direction of the induced current is such, I underline it, is such that it opposes the change in the magnetic flux responsible for its production. It opposes the change in the magnetic flux. Means if the magnetic flux is increasing, something should happen to decrease it. If the magnetic flux is decreasing, something should happen to increase it. Means if there is an increasing flux, the direction of current should be such that the flux has to decrease. And if there is a decrease of flux, the direction of the current has to be such that there has to be an increase in flux. And that will explain in diagram. It is based on conservation of energy. Now, very simple to explain in the form of a diagram. Now look at, there are two pictures here I have taken from your book. Now, when the magnet is moved towards or away from the coil, some mechanical work is done. When you move something, some mechanical work is done. This is converted into electrical energy by producing induced current. That is why I said Lenz law is based on conservation of energy. Now let us find out the meaning of that negative sign, which will give you the direction of current only. Look at this figure 1. Figure 1. This is a magnet. This is the north pole of a magnet. This is the south pole of a magnet. This magnet is pushed towards the coil. And this is the coil. The coil is not kept horizontally like this. It is kept like this. Right? The magnet is pushed towards the coil. Now, as I have explained in previous lessons, the lines of force are concentrated at the pole. There are more concentration of lines of force here and here. Suppose in this position, the number of lines of passing through this coil is 5. When this north pole moves towards the coil, more number of lines of force passes through this coil. That is, flux increases. And the Lenz law says something has to happen to decrease the flux. Then somebody has to pull this magnet towards this side. If this magnet is pulled to this side, then the flux will decrease. Now let me explain you again. This magnet, the north pole is coming towards this coil. Since the number of lines of force here are more, as this magnet moves towards the coil, the number of lines of force passing through this increases. And this is the north pole. So this coil, when seen from this side, if the current is anticlockwise, like this, anticlockwise, then due to this, the magnetic field will be this way. So it will push the magnet towards this side. So north pole of the magnet approaching the coil in the first figure. Therefore the flux increases. So if the direction of current when seen from this side is anticlockwise, now the question is, what should be the direction of current so that it will push the magnet towards right, so that flux will decrease. By bringing this magnet towards the coil, the flux is increasing. What should happen? How should be the direction of current so that the coil carrying current will behave as a magnet and will push this magnet to this side? If from this side the direction of current is anticlockwise, then this side of the coil will behave as a north pole. So it will push this north pole to this side. Therefore the flux will decrease. So when the north pole is moving towards the coil, the direction of current is anticlockwise. So anticlockwise when seen from the right side, direction of current. Now in the second case, look at the same situation here, but the magnet is moving away. Since the magnet is moving away, the number of lines of force passing through this are decreasing. Suppose initially 20 lines of force were passing through this when the magnet was here, and when the magnet is here, less number of are passing through, because when it is moving away, the coil is coming to a region where there are there is less crowding of magnetic lines of force. So when this magnet moves to this side, number of lines of force passing through this, that is the flux is decreasing. So according to Lenz's law, it has to increase. Then how it will increase? This coil, which is carrying current, now it behaves as a magnet. If this side of the coil behaves as a south pole, this side of the coil behaves as a south pole, it will pull this north pole towards this side. That will it increase. I was taking this magnet to this side. So the flux through the coil was decreasing. So if the direction of the current in this coil is clockwise like this, then when seen from this side, this will behave as the south pole of a magnet. So this will pull this north pole towards this side. That is, it will oppose this motion by applying a force to this side, because south and north will attract. So the direction of current is clockwise. So the north pole is moving away, Q is decreasing, the direction of current is clockwise when seen from the right. So, and one thing you must remember, in a given coil, if the direction of, suppose this is a coil, the direction of current from this side is clockwise, then this side of the coil, the upper side of the coil behaves as south, and the lower side of the coil behaves as north, right? That is what you have to remember.